Good morning. We are going to discuss further on the disk-tilt approximation for the flapping motion. We will consider first the hovering flight. Recall the flapping equation for the hovering flight. So, it is formed by an inertia term, aerodynamic damping, centrifugal spring, and an external excitation. Usually, we can express the flapping motion either in the rotating system, as it is expressed here, or we can express it in the non-rotating system. How shall we do this? We can use the disk-tilt approximation. One knows there is a disk approach to study the flapping motion, which is obtained by a Fourier series applied to the flapping motion in order to transform it from the rotating to the non-rotating plane. In this sense, you see here the first Fourier series applied to the flapping motion. Of course, this depends on the cosine and sinus azimuth of the disk. How to interpret this disk-tilt? If you would have here the blade from the helicopter seen from the longitudinal plane, this is the azimuth position 0. The blade is back, and here 180 degrees. In a Fourier series, you would see that actually the disk is tilting from front to back. So the angles are becoming A0 plus A1, and this is A0 minus A1. In the lateral view, you would see the disk at an azimuth 90 degrees and 270 degrees. And if you substitute the expression of the psi in the Fourier series, you would see that the disk is tilting also to the azimuth where psi is 90 degrees, to the right. So, we have transformed the flapping hinge motion from the rotating system to the non-rotating system. Now, assume that no flapping dynamics is associated in the disk. Going back to the Fourier transformation, we can calculate the acceleration of the flap and the velocity of the flap and the acceleration of the flap. Of course, because we know that the azimuth is omega t. These formulas can be substituted into the initial flapping equation into the rotating system, and then we can collect the free term, the cosine, and the sinus term. In this way, we obtained a new equation which represents the motion in the disk-tilt system. If we equalize each term, we obtain three equations. The first equation gives the free term and represents the coning angle. The second and the third equation, one can see for hovering flight that they have no solution, that the B1 and A1 are 0. It follows that for a hovering helicopter, seen in the non-rotating system, we see the so-called coning angle, which depends on the blade log number, on the collective pitch, and on the inflow of the helicopter. And then it will be a longitudinal disk tilt of the cone, longitudinal A1, lateral B1. However, in hovering flight, this longitudinal and lateral tilt are demonstrated to be 0. So we transform now the flapping motion from the rotating to the non-rotating system, and this will be used in building a simulation model for flight dynamics.